In this video, we will learn to calculate temperature coefficient of resistance of the material of the wire using a Carey Foster's bridge, and also we will draw temperature resistance graph, and from that we will find alpha. So these are the experimental observations obtained. The first part of the calculation involves finding rho, that is the resistivity of the Carey Foster's bridge wire. So here we have the set of readings. Here it is the R 0.1, and then we have L1 and L2 here, then L1 difference L2, then we have to find what is rho. Look at the first set of reading. R is 0.1, the L1 is 45.5 and L2 is 55.6, and L1 difference L2 is 10.1. Then we have rho, which is given by R divided by L1 difference L2. Many students do not know what is this L1 difference L2. We have two readings here, L1 and L2. L1 difference L2 means you can subtract a smaller number from a bigger number. So it is up to, depending upon the number, it is L1 minus L2 or L2 minus L1. So we have to subtract a smaller number from the bigger number. So that's what this L1 difference L2. That means we are taking the difference between the two numbers only. We are taking only the magnitude. So for first set of readings 0.1, L1 is 45.5 and L2 is 55.6. So L1 difference L2 is 10.1. 10.1 into 10 power minus 2 meters. Exactly saying with units, it is 10 power minus 2 meters. So rho is equal to R, that is 0.1, divided by L1 difference L2 is 10.1 into 10 power minus 2. So when this 10 power minus 2 goes to the numerator, it becomes 10 power 2. So R divided by 0.1 divided by 10.1 will give us 0.0099. For the second reading 0.2, the L1 is 41.9, L2 is 60.2, and L1 difference L2 is 18.3 into 10 power minus 2. Again calculating in the same way, we get the resistivity rho as 0.0109 into 10 power 2 ohm per meter. In the same fashion, we can calculate all the rho for all the other values. We get 6 rows here. Now let us check the row values of the rho here. When I check all these 6 values, I find the first one seems to be odd or different from the other 5 values. So I have highlighted in the red color. So looking at the other 5 values, you could see the rho comes around 0.013 or closer to it. The first value seems to be a smaller value when compared to all these values. So I have neglected the first value while taking the average. So in your notebook, if you find that one particular value seems to be smaller or higher than the other, you can neglect it and you can highlight it by putting a cross mark near to it. So I have left the first value and taken the other 5 values, added these 5 values and divided it by 5 to get the mean rho as 0.01288 into 10 power 2 ohm per meter. Okay, so the next part of the experiment involves the finding the resistance of the coil at different temperatures. It is enough to find resistance at 2 different temperatures to get the temperature coefficient of the resistance of a coil. But here we have found the resistance for 3 different temperatures, one at ice point, one at normal temperature, that is at room temperature, and at boiling temperature. So this is the tabulation involved finding the resistance of the coil at 0 degrees, at ice points. So in heading it was written room temperature by mistake. So this is found at ice temperature. So the first reading taken during the experiment is the middle value, which is highlighted here in red. So for the we got the null deflection at 50 for the resistance of 8.7. When we interchange it, the balancing length comes out to be 51.5, and for that value the corresponding resistance is 8.7193, which is corrected to the fourth decimal. Okay, how to calculate this x1? I mean the resistance at ice temperature is taken as x1. How to calculate it? The formula goes like this: x1 equal to r plus or minus L1 difference L2 into rho equal to. So for the middle value we have plus or minus. We always have a doubt whether to take plus or take minus. For the middle value you have to take plus. So 8.7 plus L1 difference L2, 51.5 minus 50, so 10 power minus 2. The rho is 0.01288 into 10 power 2. Here this 10 power minus 2 and 10 power plus 2 will get cancel each other, and you will get 1.5 into 0.01288. When you multiply these two numbers, you will get 0.0193, that is added with 8.7 to get 8.7193 ohm. So for the null deflection at 50, I mean for the balancing length at 50, the accurate or the measured value of resistance is 8.7193. The trick here is the trick here to how to use the formula is the readings above 8.7 and all, we have to use x1 equal to r plus L1 minus L2 into rho, or that is L1 difference L2 into rho. And for the readings below 8.7, you have to use the formula as x1 equal to r minus L1 difference L2 into rho. So this is the simple trick here. For the center reading, you have to use the formula x1 equal to r plus L1 difference L2 into rho. And for the readings above 8.7, that is the middle reading, you have to use the formula x1 is equal to r plus L1 difference L2 into rho. And for the readings below 8.7, that is the middle reading, you have to use x1 is equal to r minus L1 difference L2 into rho. So this is the trick that has to be learned here, and you have to also see to that this L1 plus L2 is almost equal to 100 centimeters. Look at the each readings here. So it is not necessary it should be exactly equal to 100 or it should exactly equal to 100. See to that it is almost equal to 100, around 99, 98 or 101, 102. You can check in all these reading that L1 plus will always comes out to be closer to 100, comes out to be a value closer to 100. So in each set of reading we can see that. So using the formula x1 equal to r plus or minus L1 difference L2 into rho, we will get 5 different values of x1. In all these values you could see that x1 comes out closer to 8.7, and taking the average of all these 5, you will get x1 is equal to 8.6857 ohm. So this is the resistance of the coil at ice temperature, which is measured at 5 degrees centigrade, and its value is 8.6857 ohms. The next is the resistance of the coil is found at 29 degrees centigrade, that is at the room temperature. Again the same procedure has been followed and the readings are calculated, and a mean is taken for the average value, for the values of x2, which comes out to be 9.5959 ohm. So you can see at ice temperature it is around 8.6 and at a room temperature it is 9.5, which means as the temperature increases the resistance also increases is also maintained here. In the same way, next we are going to find the resistance of the coil at the boiling temperature, that is at a very high temperature. We couldn't achieve the boiling temperature, I mean to 100 degrees centigrade, so we have taken the resistance of the coil at 85 degrees centigrade. Again the same procedure has been followed here. For the 11 point, I mean for the 50 balancing point, we get 11.5 as the resistance, and by interchanging the coil we got L2 as 48.3. For X3 it is, the middle value of X3, it is equal to R plus L1 difference L2 into rho. For the values above we have used R plus, and for values below we have used R minus L1 difference L2 into rho. By calculating by this way, we got the value of X3 as 11.4043, 11.4476, 11.5218, 11.4866, 11.4952. Averaging out all these values, we got 11.4711 ohm. So again this clearly states as the temperature increases, the resistance of the coil has also increased. Okay. Now here we have tabulated the temperatures and the resistance. The temperature of, at 5 degrees centigrade, the resistance of the coil comes out to be 8.6857. At 29 degrees centigrade, it is 9.5959. At 85 degrees centigrade, it is 11.4711. So it is clear, as the temperature increases, the resistance also increases. These are the tricks you have to keep in mind while doing the experiment itself. So it is enough to find alpha to have two resistances, but we have resistance for 3 different temperatures, so that we can find 3 different alphas by making the different combination of the resistance. So we have found 3 alphas here. So for the alpha 1, I have taken the first 2 temperatures. So the formula goes like this: alpha is equal to x2 minus x1 divided by x1 T2 minus x2 T1. So here x1 is 8.6857, x2 is 9.5959. The corresponding temperatures are 5 degrees centigrade and 29 degrees centigrade. So putting the values of x2 and x1, so it is 9.5959 minus 8.6857 divided by 8.6857 into 29 minus 9.5959 into 5. Then subtracting the numerator and multiplying the denominator and subtracting, we get 0.9102 divided by 203.9001. So alpha comes out to be 0.0044 per degree centigrade. So this is the first combination for alpha. The next combination is between T2 and x2 and x3. So that is calculated as alpha 2. So alpha 2 is x3 minus x2 divided by x2 T3 minus x3 T2. So x3 is 11.4711 minus 9.5959 divided by 9.5959 into 85 minus 11.4711 into 29. Subtracting the numerator and multiplying and subtracting the denominator, we get 1.8752 divided by 482.99, and alpha 2 comes out to be 0.0038 per degree centigrade. Again this value is also closer to alpha 1, which is 0.0044 per degree centigrade. Again calculating alpha 3 by taking the other combination, that is by taking the resistance at the ice temperature and the high temperature, we get the alpha as 0.0040. So now we got 3 alphas. So the mean alpha is taking the average for these 3. So it is alpha 1 plus alpha 2 plus alpha 3 divided by 3. So all these values are closer to each other, so we can average out these three values. It is 0.0044 plus 0.0038 plus 0.0040 divided by 3 will give the alpha value as 0.0041 per degree centigrade. So by calculation method, we got the temperature coefficient of the resistance of the coil, material of the coil, to be 0.0041 per degree centigrade. Next, we will check whether we are getting the same values by drawing the graph. So the graph is drawn by taking temperature along the x-axis and resistances along the y-axis. So the appropriate scale is taken. The appropriate scale here is on the x-axis 1 centimeter is taken as 10 degrees centigrade, and on the y-axis the 1 ohm is taken for every 1 centimeters. So each 1 centimeter will give you 10 degrees, will represent 10 degrees centigrade, and each on the x-axis and on the y-axis each 1 centimeter is 1 ohms. Next, let us plot the graph here. So for 5 degrees it is 8.6857. And for the 29 degrees it is 9.5959, and for the 85 degrees it is 11.4711. So all this graph is plotted here. Then then join the you will get a points like this and join it using a using a scale. You will get a straight line and make that straight line to make an intercept in the y-axis. Here the straight line cuts the y-axis at x0, at a point which is named as x0 here. So the x0 value is 8.3 ohms here. This 8.3 ohms here. Then take a slope for this. When you take slope for this, you will get dx by dt. So dx by dt is, dx by dt in the sense, the slope is dy by dx. Along dy we have dx, along dx you have dt. So it is 2.1 here divided by 59 centimeters. So you get 0.03559 as your slope. So using this value you can find the value of alpha from the graph. So the formula is alpha is equal to 1 divided by x0 into dx by dt per degree centigrade. So x0 we got it as 1 divided by 8.3 into dx by dt is, that is the slope, 0.03559, and we got the value of alpha as 0.00428. So we can present our results as the temperature coefficient of the resistance of the coil, resistance of the material of the coil. By calculation method, this alpha is equal to 0.0041, and by graphical method is 0.00428 per degree centigrade, which seems both the values from calculation method and graphical method are similar or same.